This topic is two-dimensional kinematics, otherwise known as projectile motion. The section that we're covering first is called horizontal projectiles, and I will first deal exclusively with horizontal parameters. Now, we have some vocabulary that we need to introduce for this topic. The vocabulary would be projectile. A projectile is a moving object. Generally speaking, it was fired or shot. It might be a bullet, a cannonball, an arrow from a bow and arrow. It could be a car driving off of a cliff. It could be a marble rolling off the edge of a table. But once it leaves the cliff, the top of the building, the table, it becomes a projectile. The trajectory is the path followed by the projectile. And I will show you a diagram of a typical trajectory in just a minute. Generally speaking, a trajectory is shown with a dotted line. The other vocabulary word is the word range. Range, the symbol for range would be dx for distance in the horizontal direction, and that would be the horizontal distance covered by a projectile. Generally speaking, the easiest way to measure this is right along the ground. Let me show you a diagram of these three vocabulary words in action in what could be a real problem. Let's draw a cliff. All right, out west there are big mountains, and if you stand up on top and look down, you're looking over the edge of a cliff. C-L-I-F-F. You don't want to fall down. You'll get hurt. So let's say that you fire a gun, all right? This guy has a gun, and the bullet is fired horizontally. It immediately starts to fall down, so the bullet is the projectile. The path that the bullet follows is the trajectory. Right, now, if I had more room, I would stretch it out a lot more, but this is a short board. And the range is most easily measured from right here at the base of the cliff to here, where the bullet hits. This would be dx, or the range of the projectile. So those are our vocabulary words in a real problem. Now, let me show you all the different examples of horizontal projectiles that tend to come up in basic physics problems. You could have a table. All right, here's a table. There's the legs of the table. And here's the ground. And a marble is rolling horizontally along the table, and when it gets to the edge, it rolls off the table horizontally. And that velocity, that initial velocity, would be Vx. And the marble would immediately start falling down right away as soon as it gets off the edge of the table. You could have a building. All right, and here are the windows of the building. And here's a guy with a bow and arrow, and he fires the arrow horizontally. Here are the feathers at the back of the arrow. He fires the arrow horizontally. That's your V, your initial velocity in the x direction. Same thing here. Initial velocity in the x direction is exactly horizontal. It's not fired down at any angle. It's not fired up at any angle. It is fired exactly horizontally. And the arrow immediately starts to fall down. So we have a marble rolling off a table. We have anything fired horizontally from the top of a building. We have a cliff. You could have a car that drives off the edge of a cliff. Don't try this at home. So the car drives off the edge of the cliff and immediately starts to fall down. The car has an initial velocity in the x direction. You could also take, for example, a pitcher, a baseball pitcher. The baseball pitcher, right, can throw that pitch nearly horizontally. We're going to make believe that he can actually throw it exactly horizontally. So here's the baseball, and he throws it exactly horizontally. And it immediately hits the ground. The baseball immediately starts to fall down. Maybe he's a better pitcher than that. And if he throws it a little faster, it doesn't quite, all right, maybe he's more like that. All right, and maybe it actually gets to the batter before it's a foul ball. Not a foul ball, what do you call that when, not a strike. Oh, I don't know enough about baseball to know. I know 4 of those and you walk. Anyway, so you see all the situations where an object initially has only a horizontal velocity. All right, so now let's start looking at some problems with situations where an object has only an initial horizontal velocity. Now, I want to make something clear. This won't be important until the next section, but I'd like to make it clear right now. Whenever an object is fired exactly horizontally, like that, the initial vertical velocity, that's the velocity down, is 0. If you fire an object this way, whether it's a cannonball, a bullet, a car driving off the edge of a cliff, a marble rolling off the edge of a table, a pitcher pitching a ball exactly horizontally, you've got an initial horizontal velocity, which might be, for example, 10 meters per second, but the initial velocity down is going to be 0. All right, this is going to take a little bit of getting used to, but in this section, we are only going to talk about the horizontal parameters. I'm not going to get into the vertical parameters until the next section, the section after that, and probably the section after that. So again, when an object is fired horizontally, the initial velocity down is 0. You're not firing it at a downward angle. You're not firing it at an upward angle. You're firing it that way, and there is no velocity down and no initial velocity up either, for that matter. The only initial velocity is in that direction. So really, it's the same as if you were just dropping the object. It's the same as if you were dropping the object. The initial velocity up and down is 0. All right, here we go. Now, let's start with a cliff. All right, here's a cliff. And I'm going to deal with situations where we know how long it's going to take to hit the ground. In this section, we know the time to hit the ground. In the previous topic, in one-dimensional kinematics, acceleration due to gravity and free fall, we calculated how long it takes an object to hit the ground. So we know how to do it. And I'm going to cover it again in the next section, and the section after, and the section after. The calculations you need to do to figure out how long it's going to take an object to hit the ground. But for this section, we know the time to hit the ground. It's going to be a given in this section. So we have a cliff. Let's say the cliff is 45 meters high. All right, so the dy, the distance up and down, is 45 meters. All right, so dy equals 45 meters. Now, we know from the magic chart, and we know from calculations that we've done before, that it's going to take an object 3 seconds to hit the ground, approximately 3 seconds to hit the ground from a height of 45 meters when it is either dropped or fired horizontally. So let's say that this is given. The time is 3 seconds. All right? So far we've got this information. We've got the time to hit the ground, and we've got the height above the ground. Now, let's make it a gun. All right, here's a gun, and it's a bullet. All right, so there's the bullet. And the bullet is fired horizontally. Again, it immediately starts to fall down. Now, we're neglecting the distance here. All right, we're neglecting the height of the gun. All right, we're just going to say that that's 45 meters. We're going to keep this problem simple. All right, we're making believe that the gun is being fired right from the edge, right from the top at 45 meters right there. Let me just move that down. All right, so it's exactly at 45 meters. All right, now, this is the bullet is the projectile. This is the trajectory. Here is our range. The horizontal distance most easily measured along the ground, dx. All right, the range. We want to know what the range is. The question is, what is the range? In other words, how far the land from the base of the cliff. Here's the base, and x is that distance. Now, we have an initial velocity out of the gun. Let's say that it is given that the initial velocity out of the gun is, it's a bullet, it's going to be pretty fast. Let's say 200 meters per second. I'm giving you 3 significant figures there. All right, we'll make these both 3 significant figures, just for argument's sake. Not a big deal. All right, so we've got 3 significant figures, 3 significant figures, 3 significant figures. All of this is given. And we want to know dx. We want to know the range. All right. Here's where you're going to learn something that you did not know before. In order for the bullet to pick up speed inside of the gun, there is an explosion. Right? And the gas from that explosion propels, pushes, applies a force to the bullet inside of the gun. The bullet obviously starts at 0 initial velocity inside the gun and picks up speed very quickly when the gun is fired. But all of that happens inside the barrel of the gun. Once the bullet exits the barrel of the gun completely, there is no longer any force pushing the bullet that way. The bullet just heads on its way. So my question to you is, after the bullet leaves the gun, does it have any acceleration in that direction? Is the bullet going faster and faster in that direction? Is the bullet slowing down in that direction? What's happening in the horizontal direction? The answer is that the bullet has no acceleration whatsoever in the x direction, in the horizontal direction. Whatever speed the bullet has when it leaves that gun, the velocity, the speed is constant all the way through the problem. There is no little engine, like on an airplane, pushing that bullet faster and faster forward. There's no wings, like on a bird, making that bullet go faster and faster that way. The bullet continues horizontally at constant velocity. Whatever the velocity was when it exited, the initial velocity, 200, is the same horizontal velocity over here, right up to the point where the horizontal velocity acceleration in the x direction is 0. So Vx is constant because the acceleration in the x direction is 0. So, in order to calculate the range, we're going to use a straightforward equation, the simplest equation of them all, for constant velocity. And that equation would be velocity equals distance over time. Again, acceleration is 0. So even if you were to think, oh, what about this equation? Distance equals v initial t plus 1/2 at squared. I'm going to just make that vt plus 1/2 at squared. If the acceleration is 0, this whole part here goes bye-bye, right? And this equation is the same as that equation. Take this equation, you're trying to find the range, solve for d, all right, v over 1. So d times 1 equals velocity times time. Okay? Now, I'm going to say dx equals vx times t. And I am now going to call this, I'm going to give it a nickname, I'm going to call it the range equation. The range equation. dx equals vx times t. So, to figure out the range of this bullet, all right, dx is going to be the x velocity. So v initial is the only x velocity we have. It stays constant the whole time. So v initial x is vx, is v final x. The only x velocity we have is v initial x. So it's 200 meters per second times the amount of time it takes to hit the ground, because it stops going that way when it hits the ground. So the time to hit the ground, which we know to be 3 seconds, it was given, gives us a range, dx, of 600 meters, all right, for this bullet. Oops. 3 significant figures, 3 significant figures. Okay? So we just calculated the range, knowing the initial horizontal velocity, which stays constant the whole time, and the time it takes for the bullet to hit the ground, at which point it stops. It stops going down, it stops going that way. We don't worry about what happens if it bounces. All right, let's try one more problem. Let's try a cannon fired from the top of a building. All right, so here's a building. There's the ground. Here are the windows of the building. And the cannon is pointed exactly that way, exactly horizontally. So we'll mount the cannon right there. Here's the cannonball. And let's say that the speed of the cannonball out of the cannon is, I'm making up a number, let's say the problem says it's v initial x is 350 meters per second. We know that the cannonball immediately starts to fall down. Boom, hits the ground right there. All right, here's your range. dx. From there to there, from right here to right there. That's your range. The question is asking for the range. Let's say that the cannon, let's say the building is 125 meters high. All right, dy is 125 meters. And they tell us that it's going to take 5 seconds to hit the ground. All right, the time to hit the ground is given. In this section, I am dealing with problems where the time to hit the ground is given. it's going to get more complicated in the next section, the section after that, and probably the section after that also. But if you want to know how far the cannonball goes, where does it hit the ground over here, all right, then your equation is going to be the range equation. dx equals vx times t. The velocity in the horizontal direction is 350 meters per second. The amount of time to hit the ground is 5 seconds. All right? So we've got 1,500 and 250, 1,750 meters. All right, I'm just going to double check my math off on the side here. 350 times 5, 520, yeah. 1,750 meters is the range of that cannon. In other words, from the base of the building to the spot where the cannonball hits the ground, along here is exactly 1,750 meters. Let's do something a little bit different. All right, same type of problem, but this time let's calculate the initial horizontal velocity. All right, let's say we have a table. Here are the legs of the table, and let's say here's the ground, and let's say that a marble rolls off the edge of the table. All right, at v initial x. We don't know. We don't know the speed at which the marble rolled off the edge of the table. But what we do know is that it immediately started to fall down. We know that the range, all right, from here to here, all right, dx, it's given that the range is 0.60 meters. All right, the range is 0.60 meters. All right, the time to hit the ground is 0.30 seconds. All right, the time to hit the ground. The intensity of the marble. How fast it rolled off the edge of the table. So again, since we know the range, we're going to use the range equation. All right, dx equals vx times t. But I'm going to solve for v because I want to know v. So vx equals dx over t. All right, so let's start substituting in. All right, my range is 0.60 meters. All right, that's right along here. 0.60 meters. That's about that big, right? This is a meter, right? So 0.6 meters is about like that, okay? And this is less than 1 second, all right? 0.6 divided by 0.3, 0.60 divided by 0.30. So the velocity, 0.6 divided by 0.3 is 2. So the velocity of that marble, when it rolled off the edge of the table, horizontally, was exactly 2 meters per second. All right? So if we know the time and the range, we can find the initial horizontal velocity. If we know the initial horizontal velocity and the time, we can find the range. All right? In the next section and the section after, we're going to get a little bit more complicated. We're going to have to figure out the time to hit the ground. We're going to be talking about vertical up and down parameters. In this section, we were only talking about horizontal parameters. Let me just review very quickly some things that are always true when you're talking about the horizontal parameters with initial horizontal velocity. All right, first of all, the Vx is constant. Whatever Vx is at the beginning it does not change. Now that is assuming that we're not talking about a projectile, we're not talking about a device or a living thing with a motor, like an airplane or a bird. An airplane can go faster horizontally. That's not what we're talking about here. A bird can speed itself up horizontally. That's not what we're talking about. This is strictly objects that have no net horizontal force making them go faster. And we don't worry about air resistance, which would cause those horizontal objects to slow down. Therefore, since AX is 0, the horizontal velocity stays the same from the time it leaves the tabletop, the cliff top, the top of the building, leaves the pitcher's hand, etc., till the time it hits the ground. The horizontal velocity stays constant because there is no horizontal acceleration. Even a car, once it goes off the cliff, it has no horizontal acceleration. You can press that accelerator, that car is not going faster when you're flying through the air. The only time you can make the car go faster is when its tires are pushing against the ground. So, we have dx, right, which is the distance along the ground, and we've got the time, which might be given, or you might have to calculate the time. Now, the thing I want to mention to you is that to calculate the time, you have to start thinking about vertical information. This particular section was only about horizontal parameters. I'll see you in the next section.